I want to talk a little bit about history and how we got here, and then where I think we're going, and how Nomad can solve those problems, and specifically how it's different than the other schedulers we've heard about, like Apache Mesos and Kubernetes. So my name is Seth Vargo. I am the Director of Evangelism at HashiCorp. I'm an engineer by trade, so I previously worked at a number of engineering companies. You might recognize my face from the chef community. I've done a lot of work there. And more recently, I've moved into kind of this full-time role of evangelizing all of the HashiCorp tools. How many people are familiar with HashiCorp? Cool. I like when the numbers go up because that means I'm doing my job. For those of you that aren't familiar with HashiCorp, we make a number of open source tools. We're an open source company. So we make Vagrant, which is a really popular tool for automated development environments, Packer, which is a tool for building automated machine images, Surf and Consul, which is our service discovery and distributed key value frameworks built on top of Raft and Gossip, Terraform, which is our infrastructure provisioning and management tool. So our infrastructure as code. Vault, secrets management. Nomad, which is what I'll talk about today. It's our distributed application scheduler. Auto, which is our opinionated take on all of our other tools. And Atlas, which is actually not open source. That's our commercial product. But like I said, I want to talk about Nomad today. So what is Nomad? How many people have heard of Nomad? Cool. I don't know if you got this yet, but I like engagement, so I might ask you to raise your hand lots of times. It's OK. Thanks for bearing with me. So Nomad is a globally distributed, optimistically concurrent scheduler. And we've heard this word a number of times now, scheduler. But we've never really defined it in the context of technology. So I want to take a step back, and if you look up the dictionary.com, which is the source for everything, definition of a scheduler, it says that it's a program that arranges jobs or a computer's operations into an appropriate sequence. So I thought that was too specific, so I took it a step back even further, and I wanted to get the definition of a scheduler in the real world. So a scheduler is a person or machine that organizes or maintains schedules. So that's pretty standard. Schedulers are just a way to map a set of work onto a set of resources. So this is a scheduler. This is Microsoft Excel circa before I was born. And at the very basic level, a spreadsheet is a scheduler. It provides a way for us to map values, map resources onto values. So I don't know why my clicker is misbehaving. So traditionally, if we take a step back into the 90s for a little bit, everybody had their own data center. And I use the word air quotes there because some of the data centers were the closet in the office. And you gave all of your servers names because you had to refer to them. So in this case, I've chosen Star Wars themed. You always picked a theme, like Parts of the Eye or your favorite movie. That way you could remember them. So in this case, we have 4 servers. We have Skywalker, Vader, Leia, and Solo. And you, or an operator, would put applications onto those machines. So in this case, we have some Python and we have some Go. And then Ruby and Node.js take up a lot more memory, so they have to get their own server. But you also had you personified these servers. So for example, you knew that that Vader was not good. So you also had your little spreadsheet, your Excel spreadsheet, or whether it was a little notepad, and you taped it up to the wall. And you had the IP addresses and the MAC addresses, and then that notes column. And in this case, Vader just randomly kills applications. Haven't really figured out why. Don't really have time to address the issue, but we just know that happens. So when a server goes offline or catches fire, the operator was responsible for rescheduling that application and or fixing the machine, minimizing downtime. So in this case, we might reschedule the Ruby application onto Skywalker. We might reschedule the Python application, the Node application and Python application onto Solo. We're still not at resource maximization, but we don't have downtime anymore. Then, when that server is repaired, so whether it's replaced or repaired, we have to make sure that we update the spreadsheet because it's going to have a new IP address, and then we say rebuilt on 4/20/2016. And then we can start scheduling applications back on top of that. And this workflow was quite common. And then we later learned that if you give these operators pagers, they become highly available, and you don't have downtime anymore. So this obviously does not scale. It didn't scale in 1990. It doesn't scale in today's modern computing infrastructure. But it doesn't scale even worse, because we've moved into the era of cloud. We've moved into the era of on-demand applications. We've seen a lot of talks about like Lambda and serverless architecture. So having an operator have to make a decision about where an application should live doesn't scale in today's architecture. So let's talk about schedulers that have been around for a really long time. So I think this was brought up earlier, but a CPU is like the CPU scheduler, part of your operating system. Its responsibility is to map particular processes to a CPU. So here we have a 4-core machine. I have 4 processes. I have the kernel itself, Apache, Redis, and Bash. And that's all great. But let's pretend I have like a 2-core machine. So no longer do we have a one-to-one mapping. Instead, we have those resources that are vying for the same core. So it's the scheduler's responsibility to prioritize those. So in this case, what has the highest priority? Anybody want to take a guess? The kernel, right? Because if the kernel's not running, neither is anything else. So in that case, the kernel might get a dedicated core, and we might be shifting between the other 3 applications on the second core. But we might also move the kernel's operations to the second core at some point, because that's what the scheduler does. And the way it makes that decision is up to that particular scheduler and the constraints it's given. So schedulers aren't a new concept. They've been around for quite a long time. So CPU schedulers map threads to, so the work that they have to do is threads. They map them onto physical cores. In the context of like EC2 or OpenStack's Nova, we're mapping virtual machines. The work is a virtual machine, and we're mapping that onto a hypervisor. In the case of like Hadoop Yarn, we're mapping jobs, big MapReduce jobs, onto a series of nodes. And then more recently, where we start to see the word scheduler pop up, it seems like it's been defined a little bit more, is a cluster scheduler. And that's where we're mapping applications, things like Docker containers or a Golang library or a Java jar onto a series of machines or servers. Some of the advantages of a scheduler are very straightforward. So high resource utilization. How does a scheduler accomplish high resource utilization? Well, within the context of a cluster scheduler, increasing resource utilization is done using techniques like bin packing, oversubscription, and having a consistent queue for jobs. The second and kind of more important thing that a scheduler does for us is decoupling the work from resources. So everybody always talks about higher resource utilization because it's the easiest way to sell a scheduler. You can walk into your manager and say, we're going to cut your cost by 60%, and they're like, cool, make it happen. And they don't care about the actual technical trade-offs of doing so. What schedulers have actually enabled us to do is decouple our work from the resources themselves. So no longer are we operating system dependent, are we particular versioning dependent. Instead, schedulers provide us an abstraction of the work that needs to be done. And that abstraction is important because it's consistent across any type of job. So it doesn't matter whether you're doing a large MapReduce job or running a single static binary. It doesn't matter if you're running a batch job that's processing some billing information that's relatively short-lived, or if you have a long-running service like Redis or MongoDB that needs to be up all of the time. It also includes certain API contracts and standardization across them. So one of the great things that Docker brought to the community is standardization around containers, providing a consistent and reliable API wrapper around containers. And schedulers are doing the same thing around applications, right? They're providing that standard API around how to deploy and manage an application at scale. And lastly, and somewhat intangibly, is better quality of service. And this is something that's really hard to measure. Everybody talks about nines. How many nines do you have? How many nines do you have, right? But there are intrinsic things that we can't measure with quality of service, like the 99th percentile latency, or how does your application behave for a user in like sub-Saharan Africa who has 56 kilobytes per second? Can they access your application? How do you measure that? And schedulers provide us with a better quality of service coupled with things like CDNs, where we can scale out globally to make sure that our applications are accessible all across the world. We do this by providing job priorities. So earlier I gave the example of Redis versus some billing architecture. One is a batch job that runs for maybe 15 minutes. One is a long-running process that's critical to the application. Without priorities, a scheduler can't make the decision of which is more important. So it'll just randomly choose or do like whichever one was submitted first. And that's obviously not ideal because as an operator or an engineer, you're aware that the MapReduce job that's doing all of the billing could probably wait a day or an hour or even 10 minutes if it means that the Redis job or the MongoDB job can continue running. Because the application, the customer-facing application or the business-facing application that is critical has to be up and running, and so do all of its dependencies. So if a scheduler doesn't have the ability to specify priority and say A is more important than B, then those decisions can't be made adequately, and you can't provide a better quality of service. The second is resource isolation. So you don't want your applications clobbering on top of one another. And this was a problem that was experienced a lot in the past 20 years. It's the reason why tools like Chef and Puppet and Ansible and Salt are so popular, are because we had to install like 20 different applications onto a machine, and without containers or Docker containers or containerization, we had multiple Ruby versions, multiple Python versions. Managing all of that was quite a nightmare. And that's where configuration management really became popular, because managing that by hand was difficult. Schedulers and containers and VMs provide us with that level of resource isolation. So we don't have to worry about Ruby 192 conflicting with Ruby 193, and is our application using the correct version? Is our Ruby conflicting with the system version? Right? These are so many questions that have come up, and schedulers are really solving those problems for us. Schedulers also aren't a new concept. I think they're a new concept to what I call mid-tier organizations. But they're not a new concept to large-scale organizations. So we already talked about like EC2 and Nova being a scheduler. It's a VM scheduler. But Amazon also has ECS, which is their container scheduler. Google has Borg, and then some of the research Google did also for Sparrow, or Berkeley did for Sparrow as well. And then Twitter and Netflix. Netflix has Titan, Twitter has their own scheduler. And these have been around for quite a long time. They're more recently being evangelized and popularized because they're becoming more relevant as we move to cloud-based architecture, serverless architecture, and we start focusing on applications instead of machines themselves. So when we talk about Nomad, and this might be a little bit redundant, but Nomad's also not alone in the scheduler market. So you have Kubernetes, Mesos, Mesosphere, Containership.io, and a number of other schedulers are continuously being created. The primary difference, as Adrian said, between Nomad and all of these other schedulers is that Nomad is a scheduler. Nomad doesn't provide you with service discovery. It doesn't provide you with all of the bits and pieces. So the reason Nomad is really popular, is gaining in popularity, is that it's really easy to adopt into your existing organization without taking an entire bite of a particular pie. So you can adopt Nomad and continue using your existing service discovery tool, whether that's Consul, which happens to be something that we make, or something like Zookeeper. The integrations are there for it. So you can adopt purely a scheduler, avoiding that vendor lock-in and avoiding all of the refactoring that might need to occur to bring your applications into the modern era. Another key difference between Nomad and these other tools are the types of applications that can be scheduled. And I'll get into that a little bit more. So there are three main points of Nomad that I want to discuss. The first is the cluster scheduling part. The second is the deployments, and then the job specification itself. So this is the job specification, and we think this is what sets Nomad apart from a lot of the competitors. We have a very human-friendly configuration. It's JSON compatible, so you can generate this as JSON, and the Nomad parser will actually read it as JSON, so you can still do machine readable and machine output. But we have a very friendly config that looks a lot like Nginx, if you're familiar with it. Key value pairs, very human-friendly, support for comments, very version control friendly. And they're designed to be checked into version control, because your job files are really the description of your architecture. In this example, we have a job named Redis, the data center that we want to run Redis in. And the task specifies how we want to run it, where we want to get it from, what driver we want to use. and the set of resources optionally that are required. So in this case, we're specifically saying that this Docker container, which is just pulling down the latest Redis image, needs half of a CPU and 256 megabytes of RAM with a minimum network of 10 megabits per second. The job specification declares what to run, and then Nomad's responsibility is to determine how and where to run it. So in this way, Nomad is responsible for abstracting the work from the resources themselves. So one of the really interesting things about Nomad is the design and the architecture, because it's similar, but also very different from some of the other schedulers out there. So understanding the goals and constraints of a problem are super important when we consider the design. At HashiCorp, we're an academic white paper focused company. We have ideas, and then whenever we're ready to build something, we go out and research all of the latest and greatest academic papers, scholars who are writing about these particular topics. For Nomad, we had a number of requirements, and these included support for multiple data centers and multiple regional deployments. We wanted the flexibility to support any type of workload, so not just Docker containers, not just VMs. We already talked about why job priorities were so important. We wanted to use the latest and greatest bin packing algorithms, and it needed to be able to support large, massive scale, Twitter scale, Google scale, Facebook scale, but it also needed to be operationally simple, such that you could get it up and running in 1 or 2 commands. When we talk about scaling, I want to better define scaling. We want Nomad to be able to scale to thousands of regions with tens of thousands of clients per region with thousands of jobs per client. And I'll talk about the million container challenge in a little bit and how Nomad performed. But if you do the math, that's 1 million jobs. In designing Nomad, we turned to our own experience first. So HashiCorp makes Surf and Consul, which are distributed systems which run at scale in production today. Surf gives us cluster membership, gossip-based peer-to-peer membership, failure detection without a single point of failure or TTLs, and it provides an event-based distribution system. It works at massive scale, tens of thousands of machines in a single data center. It's production hardened for a number of years now, used by some of the largest companies on the internet, and it's operationally simple. Consul is built on top of Surf, and it's our service discovery framework. It allows for a distributed key value store. It also includes a number of features that are important in a distributed system, such as a centralized locking mechanism, and it uses an architecture for centralized servers and distributed clients. Consul itself is multi-data center aware. It uses Raft for consensus. It also has been tested at incredibly large scale and is very production hardened. So Surf and Consul provide us the gossip and consensus layers, and they're also very mature libraries with powerful design patterns. The problem is that they all lacked scheduling logic. And at HashiCorp, we believe in the Unix philosophy, which is you should do one thing and you should do it very well. And it doesn't make sense for a service discovery framework to be responsible for scheduling, just like it doesn't make sense for a scheduler to be a service discovery framework. So for this, we turned to academia. We wanted cutting-edge technology. We wanted cutting-edge research in the field of scheduling. And we primarily were guided by work done by Google and AmpLab at Berkeley. So a number of people have talked about Borg already, but Borg is Google's internal scheduler. I think part of Borg also runs Google Cloud Platform. And then Berkeley, Sparrow was coming out of Berkeley, which was a similar scheduler. So doing a survey of the current academia at the time, schedulers are either optimistic or pessimistic based on their concurrency. And they choose whether they want to manage state internally or if they want to push it off to something like etcd or some other service. And then they're either single or multi-level. So Borg is fixed in its scheduling logic. So like the scheduler is built into Borg, whereas Omega has a pluggable architecture. So you can bring your own scheduler. Some schedulers are highly optimized for batch workloads, so billing processing, one-off jobs, the like 5, 10, 20-minute jobs, whereas others are more optimized for long-lived services, Redis, database, job application, etc. So ultimately, Nomad is more inspired by Omega than it is Sparrow. It's optimistically concurrent, which allows it to make scheduling decisions in parallel across many of the servers. It uses internal state for coordination, both for speed and to make it more operationally simple. We didn't want the first step out of the box to be go install this other tool so that we can store state. We wanted it to be operationally simple out of the box. We focus on both service and batch workloads, and we're going to support a pluggable architecture for drivers very shortly. In starting our system design, we turned to Consul. Consul is very familiar. We knew it scaled. This is Consul's architecture at a very high level. So up on the top, you can see all of the clients. The clients communicate with each other over RPC on the LAN gossip. They communicate with servers. Those servers are responsible for 3 things. They're responsible for responding to RPC requests. They're responsible for leader election. And then they're responsible for forwarding requests to the leader if in the event they are a follower. Within a data center, the nodes talk to their local servers. But the servers also participate in the WAN gossip, or the public internet gossip. So across multiple data centers, the servers are communicating with each other over the public internet, or some resemblance of the public internet. In this architecture, the failure domain is isolated to the data center. So your failure domain is the data center itself. And this was because each data center is completely isolated from its peer. Nomad's architecture is very similar, but we've introduced this concept of a region. So a region is a collection of data centers and has only a single set of servers. So whereas in Consul, each data center has a collection of servers, in Nomad, each region has a collection of servers, and each region is a collection of data centers. So as an example, you may have Frankfurt, Ireland, and Scandinavia as your 3 data centers, right? Those are where your data centers are physically located. That region might be Europe. So region is just a higher level abstraction of a data center. And the reason for that is that scheduling decisions typically aren't made at the data center layer. They're made at the regional layer. So the way I like to describe it is that I like to think of data centers as countries and regions are continents. That obviously doesn't map one-to-one, but it gives you a good representation in your mind. In the multi-region architecture, the region is the failure domain, and the servers within that region communicate with each other. So if the United States region goes down, the failure domain is isolated to that continent. The European region is unaffected. So the region is the failure domain. This allows for n or more data centers per region, giving the user the flexibility to run a single region per data center or hundreds of thousands of regions, or hundreds of thousands of data centers per region, as if the world was one global region. The region is also the scheduling boundary. So you can't schedule a job across multiple regions in one submission. You can schedule it, but they're isolated jobs. They're independent of one another. Otherwise, that would break the failure isolation. So next, it's important to talk about Nomad's data model. And this is critical for understanding how the system actually operates. So users submit work in the form of a job or a job file. And that can either be done via the API, so you can build your own tooling around it, or you can use the command line directly. The client nodes are joined to run the tasks, and then the mapping of the tasks from a job to a node is done with what's called an allocation. That's a glossary term. And these allocations are only created by evaluations. An evaluation is basically a state change in the system. So some example evaluations are like, I added a new client node, a node went down, I've deleted a job, I've created a job. Or an allocation failed, meaning a previously successful allocation is now failing. And that might be like, let's just say somebody ripped a hard drive out of a physical data center node, and now you have less disk space than you originally did. That causes a reallocation to occur. So in this way, if we want to get technical, a scheduler can be modeled in functional notation as a function that takes an evaluation and returns a set of allocation updates, or an array of allocation updates. And those allocation updates are either created, updated, or deleted. And that evaluation itself can be a specialized system. So it can be a service job, a batch job, a system job, whatever it might be. In this way, it allows our architecture to be pluggable. So this makes Nomad an Omega class scheduler. It allows it to support the pluggable schedulers with custom logic, but makes use of the internal coordination and state system. The heavily inspired Consul architecture allows it to support multiple regions and multiple data centers very easily and at massive scale. In terms of the client, Nomad is written in Go, and it relies on clients to actually run tasks. The client supports a broad range of operating systems, including Windows, Linux, FreeBSD, and Darwin. The clients make use of fingerprinting, which if you're familiar with like Chef or Puppet, it's like very similar to like OHI or Factor, collecting data about the system that's used in the scheduling decisions, and pushes that information up to the Nomad servers. So here are some examples of the fingerprinting. So for example, the operating system, kernel, OS version, hardware, how much CPU do we have, both total and available, memory, disk, the capabilities of the system itself. Is Docker installed? Is Java installed? Is console installed? And then the environment itself. Is it on AWS? Is it on GCE? Is it on OpenStack, et cetera? The information from the fingerprints is provided to the servers to constrain task placements and support bin packing. So for example, in human terms, you would say this task requires Linux, and then as a result, implicitly Docker, and PCI compliant hardware. And all of that is expressed as a constraint in the job file. It's codified, it's in version control. When you say that my task needs half a gig of RAM and exactly 1 CPU core, that's expressed as a resource ask in the job file. Again, codified, in version control. You get the same type of collaboration that you have on applications on infrastructure changes. Task drivers live on the client, and they're responsible for executing tasks and providing resource isolation. So right now, Nomad has support for Docker and Rocket on the containerization level. But one of the things that sets Nomad apart from some of the other schedulers on the market is that it supports more than just Docker. We support virtualized workloads with QEMU and KVM, and we support standalone static binaries such as Java jars or Go binaries. So when your only requirement is you need the JVM, or you need something that's capable of running an ELF binary, Nomad can schedule that directly for you without the overhead of Docker, without the need to install Docker on the system, freeing up additional resources to maximize utilization. We are also actively working on support for Windows Server containers, Xen and Hyper-V, and C# standalone applications. So these are some of the things that you might see in the pipeline. Ultimately, Nomad is designed to be incredibly flexible, and it does so with the pluggable architecture, fingerprinting, drivers, and the job specification format. It's a single binary, like almost all HashiCorp products. So you curl, you move it to user local bin, and you give it executable, and you have installed it. It's usually 4 lines of bash code, or 100 lines of Puppet. And there's no dependencies, absolutely no system-level dependencies, and it's highly available. So one of the last things I want to talk about, and I hinted at it earlier, is the Nomad Million Container Challenge. How many people have seen the Million Container Challenge? Cool, 1 person. So we recently did a thing where we scheduled 1,000 jobs with 1,000 tasks per job on 5,000 hosts on Google Compute Engine, and they graciously provided that for free. So if you do the math there, that's 1 million, they happen to be Docker containers, running across 5,000 hosts on Google Cloud Platform. And we added constraints to all of the jobs, some of them arbitrary, just to make scheduling more difficult. The hosts themselves all had different resources, so some were like 2 gigabytes of RAM, some were 64 gigabytes of RAM, just to make the scheduling as hard as possible. So the results were pretty amazing. As you can see from this graph, Nomad scheduled over 1 million containers. I'll talk about why, over 1 million in a second, in just under 5 minutes. So if you can't see that, that's 267 seconds is when all of the containers were scheduled. What's interesting to note is that Nomad actually scheduled more than 1 million containers. This is due to, at that scale, you have like actual hardware failure, like machines literally died. We also found a bug or two in the Docker daemon that have since been fixed that at that massive scale cause race conditions. When Nomad detects that a job is no longer running, it reschedules it. That's one of the responsibilities of a scheduler. So this is not only showing the massive scale at which Nomad can operate, but also at that scale, it's still capable of making fundamental scheduling decisions like, is this job still running? No, okay, I'm going to start it again. So Negative Nancy always says no one would ever need to schedule 1 million containers. Like, someone was thinking it. Who was thinking it? Yeah, someone was thinking it. So I'm about to show you a video. And this is a video of a stress test performed on an Airbus A320. So that's an airplane. As you can see, the wings bend significantly further than any traditional flight would ever encounter. However, there's pretty much added safety and confidence in knowing that this airplane's wings can bend to, I think it's like 39 degrees or something beyond their parallel, right? That's pretty awesome. I'm going to show you another video now. So this is a video of another type of plane. Maybe. There we go. This is another type of plane which snaps the wing at about a 17-degree incline. So I ask you this. Both of these scenarios are highly unlikely, but which plane would you rather fly in? So do you need to schedule 1 million applications? No. But which scheduler would you rather use? The one that can only schedule 1,000, or the one that can schedule 1 million at scale and be highly performant? As with everything we do, HashiCorp is, Nomad is open source, and so is the Million Container Challenge. So HashiCorp /C1M on GitHub is the Million Container Challenge. All of the scripts are open source. You're free to run this against Nomad or any other scheduler, not just Nomad. So to conclude, Nomad is a globally distributed, optimistically concurrent scheduler. It uses the goal was ultimately to allow users to dramatically increase their resource utilization, decouple applications from resources or work from resources to improve their overall quality of service. So that's all I have. I do have a really quick demo, but I don't know if I have time.
You do have time.
OK, look at that. I was hoping he said no. Thanks, Adrian. Cool. So what I have here is a really small font size. So what I have here is a Nomad server that's running somewhere on a cloud somewhere. So I have this job that's running called web app. And I'm not going to dive into the job file, but it's just a Docker container. There's 2 Docker containers. One's an HA proxy load balancer, and one's an Apache 2 serving up a static web page. And it is currently running, if I ask for more information, so we can see that I screwed this up a bunch of times because you get the whole job history. But you can see that it's currently running on, I scrolled too far. It's currently running on this particular node here, so node whatever, DC whatever. And I'm intentionally doing this without service discovery. So if there were console installed on these machines, it would automatically discover them for us. But I'm doing this like pure Nomad. So what I can do is I can ask for the status of that node by its ID. So I can see everything that Nomad knows about this node. So it currently has, 750 megahertz of the CPU is currently allocated, 512 megabytes of memory, 600 megabytes of disk, and there are 0 I/O operations currently taking place. So what I want to show you is, so this is running on 10.00.11. This is where I have to cheat and log into the AWS console to get the IP address of this node. What I'm going to do is I'm going to kill this node. And I'm going to show you that when this node goes down, Nomad is going to detect that and reschedule it on another machine. So what did I say this was? 111. All right. What is it? T now? I don't know. .h, yeah. See, I'm not a sysadmin. OK, so that node is now down, and it's shutting down. And as soon as Nomad is made aware of that node's departure from the cluster, and this was a Docker container, so we also have to wait for Docker to report that the service is no longer running. And unfortunately, that's a pull-based model, not a push-based model right now. So we do have to wait for the node to leave the cluster. Once the node leaves the cluster, Nomad's going to automatically schedule that job on another machine. And it's going to do that using the same bin packing. It's going to do another allocation. So when we run the status again, we'll see another allocation take place, which will form another evaluation. And hopefully, it'll schedule it on another machine. So let's take a look at this job status. Just ask for the total status. So it says the job is running. So let's ask for the status of the web app job. So here, I don't know if you remember, but 9DC820 was the previously running node. That was the node that we killed. Now it happens to be running on a node 3724. So for example, if I run Nomad node status with no arguments, you can see that that happens to correspond to node 57. Doesn't really have a name or anything special, so it's this last node in the list. You can see that Nomad is reporting our original node is down, so it's no longer accessible. And this application has been rescheduled onto that particular machine. In this case, 57. So if we hit up 57 in the, and again, I'm doing this without service discovery, but if there was service discovery, you would be able to use DNS or some type of interfacing to query this. But this is actually that application itself. So this is that application that got rescheduled onto this host. It's 2 or 3 Docker containers running behind a load balancer. So nothing really special. I don't have a really cool demo, but I think it's super cool to showcase what happens when an application dies, and a scheduler is responsible for making sure that it's still available to the client. That's all I have. Any questions?
There are questions, yes.
Crap.
There's a question here about Windows support.
OK.
You mentioned that all your different applications run on Windows, right? But do you have any examples of it running, companies running on Windows in production and at large scale?
Definitely not at large scale for Nomad. We do have a couple companies who are running some small scale stuff on Windows. The Nomad client runs on Windows, but the Nomad server has to run on a Linux-based operating system right now. That's something that we're trying to get rid of. So we can schedule work onto a Windows machine, but right now it's not possible to run the server on Windows. There's some Unixisms deep down in the core that we have to remove before we can port that to Windows. I don't have any examples of companies that are doing it that I can really talk about, but we do have an examples repo. It's open source on GitHub where you can see some of the job files and things that are like Windows specific.
Okay, so do you see a future for configuration management like Chef and Puppet?
I do. I think that Chef, Puppet, Ansible, Salt, I think they still play a very vital role in this space. I think that...
But a different role.
Yeah, I think they're just going to play a very different role. I think as we move towards containerization, this notion of having multiple applications on a system without some type of resource isolation from either a scheduler or a container engine goes away. So things like Chef and Puppet become crucial for provisioning the initial systems. Building like these larger cluster machines, the clients themselves that have gigabytes of memory, gigabytes of RAM, CPU disk space, and provisioning those initial instances. I don't think we're going to see them as popular in like the cron-based or you run Chef on some interval or Puppet on some interval. I think it's going to be purely more of a bootstrapping process, and then we're probably going to rely on the schedulers or the container engines to make the decisions from there.
Okay, so you mentioned the concept bin packing a couple of times. What exactly does that mean? There were 3 people who asked this.
Oh, jeez. OK, so the easiest way, and I'm going to steal Kelsey Hightower's description, the easiest way to describe bin packing is Tetris. So how many people have ever played Tetris? Right, so that's bin packing. Next question.
Okay.
Now, so the idea is that in bin packing, you reserve effectively large chunks of space such that you don't always pick like the best solution. In Tetris, you don't pick like the piece that exactly fits. Instead, you pick the piece that forms another shape that might be coming in the future. So you might form a gap that perfectly fits the T shape, even though you don't have a T shape on your map, it's not the next one. Then when the T shape becomes available, you can clear 3 rows out instead of just 1. So that's kind of the metaphor I like to use there.
Good metaphor. So do you have any sort of visualization of the cluster, like we saw with DCOS previously?
So we do have a visualization tool. It's currently in beta. It is not going to be open source first. We're going to have an open source UI in the future, but as part of our commercial offering, we'll have a UI. But I didn't want to talk about it because it's paid.
Okay. What are you guys using Nomad for at HashiCorp right now?
So we have more than guys. We have female employees too. So we are running our entire production infrastructure on Nomad. Cool. So we believe in dog fooding. For those of you that haven't heard that term, it's like eating your own products. So internally, we use all of our own products. We use Console for service discovery. Nomad runs our production and staging environments. It also runs our on-premise tool. So if you buy on-prem, we actually install Nomad on your infrastructure, and that's what runs the commercial product.
Cool. Thank you. That's all the questions.
Cool.
Give
Thank
him a
you.
hand.